forward to it.
Thank you, Randy, and I want to thank Bob. I think was the first physicist at CMU I met a few weeks ago. I know you guys have been around for a while, but we are a small campus, but I think we are fairly siloed, right? Perhaps the first time you came to a business school was to meet me, right? So first I want to thank the organizers of this seminar series. I think is bringing people from across different parts of the campus. So it's an opportunity, I think, for us to see what others are doing, and I wanted to present what we're doing and get some feedback and see if you think there are some people on campus or outside campus who would be good collaborators. So that's kind of the goal. I also want to make sure that you know that I'm not a physicist. My knowledge of quantum computing is maybe 18 months old. Okay, so please don't ask any questions that require more than normal thinking. I have been told that I have it approximately correct, my understanding of it. I did read what Feynman said: if you think you understand quantum mechanics, you don't understand quantum mechanics. So I don't understand quantum mechanics, so maybe I understand quantum mechanics. So this is joint work and simply couldn't have been possible without Hedayat and Raouf. They're both my postdoctoral research fellows. Raouf has a PhD in math from École Polytechnique in France, and so as a French mathematician, he tries to do everything topos, and I try to tell him that tapas is good, but topos I don't know. So try to keep him a bit more away from French. From what I understand, French mathematicians love abstraction and deep abstraction and things of that type. So you'll see some flavor of our papers that will use Morse theory and some Witten stuff, and you say, Sridhar, how did you get that far out there? And that is Raouf. Hedayat has a PhD in electrical engineering and has been, and both of them are doing some work in quantum computing, and that's why I got them as postdoctoral fellows. Hedayat is also very familiar with D-Wave system. He has programmed in it, and so I wanted a team where we would have people with good mathematical skills, but also people who knew the machine. So that's kind of the group here. Okay, which begs the question: what am I doing in this? So I thought I'll spend the first few slides orienting you to what we do in business schools, because many of you are suspicious of whether we are a scholarly organization at all. Right? I know for decades people resisted having a business school on campus. I think some very good universities have resisted and kept business schools out of it. So I want to give you the impression, at least, that we also are intelligent people doing scholarly work. Okay, so that's a little bit of advertising of business schools to outside of business school. On a more serious note, I want to talk about why I'm very interested in this, and then give you overview of 3 of our papers which have been loaded up on archive. And then take any questions after. There are people who know physics but not operations research, and then there are people who know operations research but not physics. I thought I would spend some time giving you a background of each. So those of you who know physics, I hope it's correct, and those of you who know operations research, I think it's correct, because I've been doing that for about 3 decades. The 2 main topics I want to give you a little bit deeper insight into is how to compute something called Graver basis. I'll define it. I'll tell you why it's interesting. And then provide you an algorithm to do integer optimization that is very different from what is classically done. My long-term goal, obviously, is to see can we beat classical best in class, because I've been for 25 years developing classical algorithms, so I just want to see if I can beat myself and then have a new class of things. I'll mention a couple of theoretical things we're doing here. This is where Raouf and others come in, some algebraic geometry and topology, just to give you a flavor. And then as I was preparing the slides last night around 9 p.m., I got an email from somebody at Stanford Evidently, they have an optical annealer. His name is Peter Mahon. I don't know, you may know him. This morning I checked that he's got 3 Nature papers, or 3 science papers and a Nature paper. His PhD is in quantum physics from Stanford. His postdoc is from Stanford. And he's now moving to Cornell as an assistant professor. And he sent me an email saying, hey, I read your paper. We had posted it only like at 6 p.m. And so he sent me an email at 9 p.m. So he must have been the first guy to read the paper. And said, I read it with great interest. And can you send me your numerical testing because I want to run it on my machine. So I'll kind of mention that there is some attraction. Okay, so that's kind of the plan for today. So what do I do for a living? I try to solve real problems using cool math. Okay, this is my opening slide. That's what I do for a living. Okay, when I was young, I realized I liked math and I was very quick at learning new math. Okay, that was kind of my only strength, really. Okay, I could not play cricket. I didn't know how to dance. I can't sing. I looked at everything else I could do, and basically the only thing I could do was I could open a book in math, read it, and get it. And I thought maybe I can make a life out of this. Okay, and so usually I work in applying mathematics to solve problems that come from Fortune 500 companies. I've worked with them for many years. For about 15 to 20 years, since the turn of the century, I've been working more closely with startups because I think it's more exciting to work with startups than with Fortune 500 companies. But typically when I work with startups, the startup is working with the Fortune 500 companies, so the eventual customer is here. The question is, in what direction are you getting there? Some of you may know that I was the founder and CEO of a company called SmartOps. I ran it for 10 years. I created the space of enterprise inventory optimization and I sold it to SAP. So I'm basically a math guy who likes to embed things in software and make some money. Okay, that's kind of the summary of it. This has been recognized by the National Academy of Engineering, and 2 years ago, about this week, I got an email saying, hey, you are elected. From what I understand, it's good to be in the National Academy of Engineering than not to be. So unlike Groucho Marx or something who said, I don't want to be in a club that is, going to accept me in it, I have accepted. And I asked them, why did you elect me? And they said, we elected you for this. And I said, okay, that kind of makes sense. Okay. So summer of 2017, I started asking, is cloud quantum computing something that can be real? Okay. Will it happen anytime soon? How long will it take? What does it take to become a reality? And most importantly, can I do something about it? Right? So my primary goal was I was reading a lot of stuff on quantum computing. As you know, much of it is probably wrong. There's a lot of hype. As a physicist, you probably you get really angry reading articles about quantum computing written in Wired magazine and New York Times and things of that type. Since many of us don't know physics, we think some of it is true. But I wanted to know if we could do something more substantial in it. Okay. So I started reading books, and for those of you who are also trying to get into quantum computing, here are some books that I like. Okay, there are many books, there are many videos. So I wanted to start to learn quantum without learning Dirac notation, because I don't know about you, but Dirac notation gave me a headache. The first few times I read it. Now I think I have a good handle of the ket and the bra and things of that type. But I got this book by Reagan and Lipton, and all you need to do this is to know linear algebra, which most of us know. So if you know matrices, unitary matrices, and Gram-Schmidt orthogonalization, stuff like that, you can actually make good progress in this business. And so Reagan and Lipton is a book that has almost no physics, and the introduction says we will not use Dirac notation. So that's the first book I got. Okay, and from that I learned a few things like what is Shor's algorithm, and I really like Grover because I think it's easy to understand, and it has a very nice intuitive picture to it. And so anytime I try something new, I ask, can I do Grover in this new method, and get the same answer. Okay, so I think the simplest thing to do is to learn Grover's algorithm. Then I found this book called Quantum Computing: A Gentle Introduction. Usually when you see things like a gentle introduction, you're not sure how gentle it is. because it could say if you have a PhD in mathematics from Harvard and 2 postdocs, it is gentle. But I wanted to be gentle to a business school professor, who wants to read this while sipping a drink or something like that, right? So, but it turns out this Rifle and Pollack is actually a very gentle introduction. And later on, I met Rifle. Her name is Eleanor Rifle. She turns out to be the head of the quantum AI lab at NASA. Okay. Some of you might have seen an email I sent out. We are looking for some PhD students to do summer internships. It'll be in her group. Okay. I think Nielsen and Chong is called Mike and Ike is the classic. It is the Bible, I think, in the field. It's Michael Nielsen and Isaac Chuang, and so it's called Mike and Ike. So if you go to Google and do Mike and Ike, and boom, this will come out. Those of you who follow Google citations, this book alone has 40,000 citations. So a lot of people are citing it. I don't know if they're reading it or not. If you want to understand something about D-Wave, you can go to their website, and then you can see their hardware. And then if you really want to get in a little bit, you have to start reading some papers in Science and Nature and physics review letters and things of that type. And names like Farhi, I think Aronson, and others come up. I hear Preskill is a well-known physicist. Yeah. So what I found interesting as I was reading this was there were a lot of things that overlapped with what I had done 20 or 25 years ago. And I want to bring up a couple of those things. So a long time ago, I wrote a paper where I was trying to solve a convex optimization problem using coin tosses. Okay? By tossing the coin a bunch of times, you're going to do a random walk. And at some point, you're going to stop and you're going to claim that I'm close to optimal solution with high probability. Okay? And the math of that goes like this. Each toss is a probability step. So think of this as a Markov chain transition probability P in n by n space, right? Second step is P squared, third step is P cubed, blah, blah, blah. You go to P to the power K after K steps. The limiting distribution is some pi, and the P ij's are chosen so that the pi ij's are such that with high probability, you are in the near optimal region, right? Now the question is, how many steps K should you take to get close enough to pi? It turns out that if the spectral gap of this Markov chain, which is the difference between the two smallest eigenvalues, is high enough, then K is 1 over the spectral gap squared is the number of steps that you need. So the connection between computational complexity of such algorithms is related to, it is inversely proportional to the spectral gap. And you'll see this basically in quantum mechanics as kind of the flavor of it. Okay? And this is because we're all dealing with matrices. So I'm just giving you kind of the similarity, which has nothing to do with quantum physics. It just deals with how rapidly kind of a matrix mixes. Independent of that, one of my favorite things as a PhD student was to read algebraic geometry. There's a book called Cox, Little, and O'Shea. I believe in 2016 they won the AMS Steele Award for the best book for education. And I read it just before it came out in print in a preprint form in 1989. I'm just aging myself here. Okay? I loved it. It had no practical importance, but I loved it and I wrote a couple papers on it. It turns out that repurposing what I did 20 odd years ago is actually a very nice way of embedding problems into D-Wave. And the first paper we put on arXiv was how to use computational algebraic geometry to represent our problem on D-Wave. And this is what the NASA folks like, and what they want the PhD students for is to basically program this for them in D-Wave. Okay, so it turns out that my first paper actually is going to be used to test out if this is a good way. I'm bringing this up because the mathematics of quantum mechanics is different, but it's not that different. In the sense that if you're generally somebody who can handle mathematics and you don't think too much about what it means, it's fairly easy to catch on. So what have I learned since the summer of 2017 when I started this? Basically, for people like me, which I think of classical OR guys, You have to think differently. What I mean by think differently is you have to reframe our problem. We think of it as mixed 0-1 integer program, and that's kind of our mental model. We have to frame it into a different model, which is very well known in physics, called the Ising model. But people in operations research have never heard of Ising model. I mean, except if it's accidentally seen. It's not very hard. It's just different. It's like if you spend all your time learning Hindi and then you go to France, you have to learn French. It's not that French is particularly hard, but you have to do the translation from Hindi to French. And in some sense, the first step for people to get used to is, how do I represent a problem which is minimize c dot x, ax equal to b, x integer, which is how we think in operations research, into something that the physicist says, that's like a two-body interaction Ising model with coupling constraint Jij. And for OR people, he said, what did he just say? Physicists are all nodding their heads. So I can see from the nodding who is a physicist and who is not. Okay, I'm just giving you a broad overview, and I'll show you some of these things in just a bit. Essentially, what happens is we have to take our problem and embed it into the hardware so the hardware understands what is your problem. Then you let the hardware do its thing. The other thing that is very different for classical algorithm guys to note is, in classical algorithm, we are telling the computer what to do. In a quantum computer, you're just setting it up and let nature find low energy solutions. If you set it up correctly, that low energy solution is the solution you're going for. That is, a quantum algorithm is not telling a quantum computer what to do. A quantum algorithm is just setting up so that nature can do its thing. Okay, I am going only for the quantum annealing kind of a viewpoint.
Even for the D-wave, like, if the D-wave doesn't exist, it doesn't have its qubits, its topology, then nature doesn't do its thing.
Correct.
So, again, maybe it's a, what's the word I'm looking for, tautology? Anyway, so I would agree and disagree. The thing I find very interesting is, what is the limitation on QUBO? That is, what kind of, because QUBO is fine, and it maps to an Ising model very nicely. The question becomes, like, so what kind of problems? So that you can do, like, max cut and whatever.
So if you hang in there, let me go through, and you'll see why one of the things I'm doing differently is not trying to represent the objective function in the form of a QUBO. Okay, so one breakthrough, and that's different, and which is why another group at NASA said we like the class of your algorithm methods, is I've decoupled the objective function from what I'm doing. We're using something called test sets. I'll come to that in just a bit. And therefore, a lot of the considerations with respect to embedding your problem into D-Wave, which is passing through QUBO, which is asking the first step, can you represent your objective function into QUBO in the first place, is removed, actually. So we'll come to that in just a bit. Okay. I'll come to that in just a bit. Okay. And then, because this is hardware that spits out answers, these answers don't always make sense. Okay? There's something called chain breaking, and I want you to see this. I'm introducing these words just, and you'll see this more. Ising is known to physicists, not known to OR. QUBO is quadratic unconstrained binary optimizer. It is just a middle step you need to go from your problem into what a hardware can understand. Degenerate solutions means low energy solutions. Chain break is something I'm going to show you. It's something that comes out from the hardware. Okay, this is the essential thing. Whatever you're doing inside with D-Wave, this is what you'll be doing. By the way, I agree with you. I'm doing very much D-Wave. My guys are also working on similar things for gate, and a future talk, maybe I'll do that. So today I'm limiting myself really to this kind of quantum annealing procedures. So because I like cool math, I said, okay, we're going to write 3 papers. So our first 3 papers said, can we do the embedding, which is basically the compiling of the problem, very differently from what D-Wave is doing. Okay, D-Wave has a graph-to-graph. It has a heuristic. It's a graph-theoretic heuristic. It works well many times, but many times it doesn't work well because the underlying hardware, which is a bunch of qubits connected by links, is not a complete graph. It is actually a very sparse graph. So to even represent your problem, I'll give you a simple example into the graph, requires some tinkering of your problem so that it fits in there. They have a heuristic that says, if you give me the problem, I will tinker it for you and fit it in there. But when we started playing with it, we saw two types of problems with the D-wave heuristic. By the way, I work with them every other week, so I know this. Sometimes it says you cannot embed it, but I know how to embed it. So you know the heuristic is not searching entirely. And two, sometimes it embeds things, and it's very clumsy embedding. By clumsy embedding, it creates longer than necessary chains, okay? And you'll see that. So we said, what if we were able to do it better, at least for small problems? And that's the first paper. And that is where I am repurposing the algebraic geometry I used to do 20 years ago. Okay? Those of you who know algebraic geometry, there's something called toric varieties. There's a Grosvenor basis of toric varieties. We basically reframe the problem of embedding as a Grosvenor basis of toric varieties, and boom, we get the answer. Okay? Separate from that is to understand how you analyze quantum speedup. It has to do with spectral gaps. And so a lot of fascination in adiabatic quantum computing is to say, as you are changing your Hamiltonian from an initial Hamiltonian, which is very easy to prepare, whose ground solution you know, and letting it slowly change, it's called slow time, slowly into the problem Hamiltonian. I'll show you the picture, the equation just a bit. You will pass through a region where the spectral gap, the lowest energy state and one level higher state, will get closer and closer and closer. And you have to go slowly because you want to pass through that, as slowly as possible. So if you think about how long does this algorithm take, it is related to how close these eigenenergies come together. Okay? I think they're called anti-crossings, and Wigner, von Neumann, and others have done some work on this. So physics people know all of this. But how it translates into computational time and complexity is the faster that thing shrinks as a function of n, the slower and slower you have to go. And therefore, a lot of people are thinking about, can I do something to make this gap remain large? So the whole body of work there. And Raouf really wants to upgrade that work, and so he is bringing in ideas from surf theory and modes theory to study those papers. Okay, so some of those we have put up in there. I am this guy, right? I am the nonlinear integer optimization guy. And one idea in nonlinear integer optimization is something called test sets. I'll come to that in just a bit. It's called an optimality certificate, and I want to use this method on a quantum computer. Okay, and what is my final purpose? To do cool math and to see if I can do one more time what I did with SmartOps to develop and commercialize this tool. Okay, so that's kind of the orientation of it. I'm not going to go all the way back to 1917, but I want you to know that I know these words. Okay, essentially. This is way before Dirac. There is no relativity. This is, I think, it's called Montessori quantum mechanics, which is you only worry about Schrodinger's equation. Okay, you don't worry about E equal to mc squared and things of that type, right? And therefore, there is no Dirac, right? So this is like way before. This is in some sense first cut. What I call pre-kindergarten quantum mechanics. That's all you need actually at this stage. Okay. Basically, we are trying to use something called adiabatic quantum computing. I think I've said this before. You're going to get 0, 1. And this is the problem Hamiltonian. There is an initial Hamiltonian which is easy to prepare. And then you're going to start with s equal to 0 and go to s equal to 1 or some other function of s. It can be some g of s. But you have to go so slowly. It's almost like the ground state is there. The Hamiltonian is changing so much. The ground state is remaining, ground state is remaining, ground state is remaining. You come to the final Hamiltonian, look at it and say, hey, I found the optimal solution. Okay? You're basically trying to make sure that the ground state is not disturbed, and you have to go through it very slowly. That's kind of the business school intuition of what is happening. There are a couple of limitations. The kinds of hardware I think that D-Wave and others are building are not universal, in the sense that a qubit is going to interact with neighboring qubits. It's called a two-body interaction. Okay? To make a universal quantum computer, I think you need different architectures. And so this is already not universal. Okay? So I think you take that off the table. The only question we are asking here is, with this kind of architected hardware, what can you do today? Okay? And from what I understand, is generally feeling that the icing architecture is going to be largely the type of architecture that we're going to see, at least in the near future. Okay? So I'm going to show you one slide that will look more like a physics slide than an OR slide, and it's going to look like this. Right? So physics people know what a Pauli matrix is, and you say, sure, I can see this in my sleep. For an OR person, you say, I'm sorry, is it a slide from a wrong presentation? Right? But what I'm saying is, the HIs and the JIJs are the parameters that we need to give. And so when we have minimized C dot x, AX equal to B, X integer, that somehow has to become these HIs and JIJs. That is what I'm saying is the reframing from operations research to physics. Once it is in the form of HI and JIJ, converting it into QUBO is immediate, and embedding the QUBO into the hardware is, as I mentioned, requires a little bit of skill. So when I said reframe your problem, and I'm telling the OR students here, is whenever you look at a problem that looks like an optimization problem that we have learned for so long, you have to say, if I wanted to write it in this format, what are the HIs and JIJs? Yeah.
So is that the definition of your Hamiltonian?
Yes.
I know nothing about physics. So those Jij and HIs are determined by the problem.
Correct.
And as you change the S to go the trajectory, do they also change or?
No. No.
What is changing as you vary?
HS is changing.
Oh, I see. It's a
So what you're embedding is actually HS, right? And then it's going from S equal to 0 to 1.
And you can decode the solution from it.
From H, correct.
Does it give you some optimality guarantee?
I'll show you what it does, and we can see what it is. But this is the basic idea. Okay. In principle, it's supposed to give you the answer. Now it's physical hardware, so it gives something. Okay. We have to then look at it and say, what is this thing? Okay. And when it gives it correctly, it is correct in the sense that if the physical thing works correctly, it will give the answer. It will find the lowest energy state. Okay. You will notice something in the paper if you read it already. It would have said for D wave to be competitive, its coupler precision should be improved significantly. You might have seen that in my write-up. What it means is the ability to represent Jij, many different types of Jijs should be possible. Because what happens is when I take the matrix AX equal to B, and A has many integers and B has many integers, these Jij values that are needed can be in thousands. Which means that you should be able to have a fidelity of the compiler of so many bits, say to the power 10 bits or so. Otherwise, you can't represent the different Jij. Part of the problem you're going to see as you go through is not only that the number of qubits are not very large, or that the connectivity is sparse, but the compiler precision, which is the number of bits of different Jijs that you can put, are also limited. Which means that right now we can solve only a certain size problem with respect to number of variables, and also only represent some kind of matrices A where the total number of Jijs, distinct Jijs that you need, can't be very different.
Do you know how they change the Jijs in the machine physically?
They told me, I didn't understand. So I would say I don't. But let me continue on what I know, and then we'll make a list of all the questions for which somebody else would have to answer this. I think Hadayat would know, but yeah. They explained it to me, and it didn't make any sense. So the D-Wave hardware is like this. This is the a graphical representation of it. Each of this is a qubit, and these are the links. And so this is called the chimera graph. And so whatever problem you have to embed it into this chimera graph. The new chip that's coming called Pegasus, you will see, is vastly superior to this in two ways. It has many, many more circles, but most importantly, it has many, many more connections, which is actually what is really important at that level. And then what they need to do next is to increase the fidelity of the connection. So think of, at a very high level, you say, how many qubits, how well are the qubits connected, and what is the coupling precision? Those are the three things you want to look at when somebody says, I have a quantum computer, at least as a first cut. Okay? So really, yeah.
The X and ground set, are they related to this graph? From the previous slide, so you mentioned in the description of your problem,
Yeah.
So you have the big X.
Yeah.
That's a representation of your problem.
Yes.
And then you mentioned something about ground state. Sorry. Are those things related to that graph that you?
Yes. So I will show you, starting from end to end, I'll show you a problem going from problem to embedding. So you'll see. You'll see. Okay. Oops. You have to reduce to QUBO. Somebody asked, can you reduce everything to QUBO? But for now, let's say we reduced it to QUBO. You have to embed it. I'll take a QUBO and embed it. And then there's something called chain breaks, and I'll show you what chain breaks are and recover from it, just to give you a flavor of what it is that is being done. So let me start with a very, very simple problem that we want to solve, which says I want to minimize y0, y1 plus y0, y2 plus y0, y3 up to y0, y8. It's quadratic. Y's are 0, 1s. It's unconstrained. And C's can be positive or negative, and therefore you have to be a bit careful as to which side you want to go, maybe. Right? I'm not saying it's hard to solve, I'm just saying what it is. And you say, I want to solve this problem on D wave. I don't want to solve it by hand, I want to solve it on D wave. The first thing you will notice is y0 has a degree 8 because y0 is connected to y1, y2, y3, right? But chimera has a degree 6. So you can't just put it. You will have to make a copy of y0, and first one y0 might go to some y's, the second y0s will go to other y's, and these two y0s should be tightly coupled because you want them to have the same answer. That is called a chain. As you have higher and higher order problems with y's, and you're trying to represent it in the graph which are the x's, you will notice that you have to make a lot of copies of these y's and create these chains and embed it, and therefore what goes into the hardware is copies of different y's connected but tightly coupled when they have to be the same, sending it in and telling D-Wave, these strong things, they better be the same. And the other ones, they have to be like the JIJs that I want to give, and rescale these babies so that it finds the answer. Again, I don't know too much detail, but that's the flavor of it. So what D-Wave gets is basically a whole bunches of x's of those qubits which are connected or not. Each of those x's will have an HI, and each of those links will have a JIJ, including, almost like in OR we call it the big M constraint. Here you're going to have these y's have to be the same constraint, very strong coupling. That's what it receives in some sense. You see? So for example, if I want to embed this graph into this graph, I'm going to make a copy of the y0, and some of the y0s I'm going to connect to this, some of this I'm going to connect to this, I'm going to connect these two, and that is going to be embedding y into x. It's a pure graph to graph problem. It's a graph minor representation. It's a graph problem. It's a graph theory problem. This has nothing to do with quantum computing, nothing. It's just a graph to graph. I'm just trying to represent the problem.
And what we want is this translation to embedding to not be very costly.
Correct.
We're trying to compute problems that, in principle, are maybe NP.
Correct.
We need P time translation. So is that what happens here?
No, it doesn't.
It doesn't do
No.
P time translation?
No, it doesn't. What we have here is a method that says, I know how to do it And if it says there is no answer, there is no answer. And it finds all the answers. So this is just a playground to say, how would I create a good high-speed embedding, which is better than D-Wave, but it's not this. Okay, so think of this as D-Wave has a embedding procedure. This is the fully possible extended procedure, which we are not going to do for large-scale problem. We just want to pick something in between. Okay.
To actually have this stuff be useful, one has to have an efficient way of.
Correct. Correct. There is a way of restricting its search by saying chains cannot be length more than 3 and things of that type. But it might come back and say there is no answer, although there is an answer. Right? That's kind of the trade-off you have to make. Okay. So think of this as there is a baseline method. There is this thingy which we call a sandbox, and we want to see if we can take the baseline and improve it and keep that improvement still fast enough. Okay. What happens is if you take problems with long chains and so on and so forth, when you look at the final answer, you will notice that some of these chains are broken. That is the reality of the physical piece. You told it, hey, keep it all the same, but ran it for 290 microseconds or milliseconds, and you looked at it, and you notice that these things are broken, and what we normally see is anywhere from 28% of the solutions, the chains are broken. So when somebody says, first of the issues is about a third of the time, the answer is not even correct. Forget being optimal. When it's correct, in the sense that it is not broken, I'll show you, it finds optimal solution about 63% of the times and near optimal solution about 20% of the time, because it takes we stopped it after 290 microseconds. Okay, so reality of it is it finds broken solutions. You have to do some chain break recovery. It finds some solutions that you can check, yep, they are optimal. And it finds many solutions that are near optimal, which we actually take advantage of to say, well, you came close enough, let me handle it. I don't need you to give me the optimal solution. I have a filtering post-processing, which won't take too long if you come close enough. Okay, so my mental model is I want to take a problem, represent it into hardware without it being too costly. I want it to run for a while. I want to take some answers that come out of it. If its chains are broken, I have some heuristic to recover the chain breaking. If the chains are not broken, but they are not optimal, because I can check the way I've set it up, I can do some amount of tinkering if they're close. And so the hybrid classical algorithm has a classical front end, a quantum middle, and a classical back end. Okay, that's what it is. So for example, I now want to solve a nonlinear integer program using this framework. I have some fx, I have ax equal to b, x is integer, there are lower and upper bounds. People in operations research should say, I understand this slide. There are many, many ways of solving this problem. One way that we want to explore, and you'll see in the paper why there's some benefit, is called using a test set called an augmentation procedure. It goes like this. Suppose you're given a test set, and obviously we have to find it, and that's one of our subroutines. And you have a feasible solution. For these types of problems, the feasible solution is also hard. So we have two calls actually to a quantum computer. The one call to get test sets, and a second call to get a feasible solution. So it's a two call, okay? What happens is, once you have a feasible solution, you take steps in the direction that are given by this augmentation procedure. It doesn't matter in what sequence you take them, it doesn't matter where you start. If you come to a point and you say, I cannot go anywhere that is improving or feasible, it's guaranteed to be optimal. This is called the optimality certificate. Okay, so there's a whole bunch of mathematicians, applied mathematicians in Germany and others, who study optimality certificates and test sets because they're mathematically interesting. Clearly, nobody would use it in a classical algorithm because computing the test set is very, very hard. My thing was, maybe this is where a quantum annealer can come in, and so we have figured out a way of embedding a QBO, which is fairly easy, spending 290 microseconds and grabbing a bunch of things and filtering it, and we get about 68% of the test set in about 3 seconds. Okay? Then we say, aha, where did you get stuck? We make some adjustments. So if you want to call it a second time, a third time, because we said we'll call it 4 times, we'll get it all. But you'll see that sometimes it is enough to call once, because you don't need to find all the test sets, elements, because I'm going to find a lot of feasible solutions. And as long as I have a bunch of feasible solutions and a partial test set, right? This is kind of good enough for me to find the answer most of the time. So that's kind of the 2 call minimum method. Each call is about 3 seconds. Okay, in this time frame. So if I told myself I'm allowed 6 seconds, what can you do? Plus some, classical time, which let's say is 1 second or 2 seconds. What can I do? So typically, much of what we have done with respect to comparing with classical algorithms is, if we can represent the problem and you have about 8 seconds, what can you do? Most of the time, we can't compete with classical algorithms because we can't represent the problem. The JIJs are too many, so the coupler is not there, precision, or the number of qubits required for us to do the embedding is not there. So right now, when I play with D-Wave, the problem is that many of the interesting problems I cannot embed. If I can embed the problem, I get a pretty good answer. Okay? And many times I don't get an answer competing with classical because I can't embed it. But when they showed me Pegasus, because they have given the architecture, I know what more I can embed. Right? But still, they haven't told me what is the improvement in coupler frequency, so I don't know what else I could embed. So if you look at the paper, you'll see that we played with D-Wave and we said, look, this is if you have 50 0-1 variables and you have objective functions that come from finance, which in Gurobi under some things takes 8 hours to solve or 6 hours to solve to optimality. If this baby can be embedded, it will take 8 seconds. Okay? The problem is we can't embed most of the interesting problems right now. Yeah.
Oh, so when we're talking about optimality, you were talking before about, so when you're talking about solving these, I'm not sure what kind of class this problem falls into, or classically what the algorithm looks like to solve it, but typically pick a problem like MaxCut, you want the problem solved faster, but you also have to work on approximation ratio. And now we get into what is it?
No, here it's optimal. There's no approximation ratio. So it'll find the answer. Yeah.
So classically, this is
very hard.
Is NP?
Yeah, absolutely.
So, but even then.
But remember, I'm coming from the perspective of I'm Goldman Sachs. I want to solve this problem, and so whether it's exponential or not, I want to solve it in X minutes. And I'm asking, what would it take for new D-Wave architectures to beat what they're doing today? Right? That's all I'm asking right now.
Yes, but you're also talking about optimality and finding global optimal solutions.
Correct. And some of the results you'll see here, why we chose this, is this technique is guaranteed to give the global optimal solution for a vast class of objective functions. And so that is why I chose this. The objective functions can be nonlinear in many, many ways. Think of it basically as being called as an oracle. And the test sets are there. I mean, if x is a test set, because we're going to use ax equal to 0, which minus x is a test set. So x or minus x you're going to choose, right? And so you find the test set, you start a feasible solution, you take the oracle and say, do I move up or do I move down? And if you say, look, there's nowhere to move that improves it or it's feasible, you are done. That's the procedure. Okay? If you have all the Graver bases, it is guaranteed to optimal solution with one feasible solution. If you have all feasible solutions, you don't need Graver bases. So what we find is one call to D-Wave gives us 6,000 feasible solutions. One call to D-Wave gives us 68% of the test sets. We say enjoy with one call each, and pretty much it finds the answer to problems which it can embed and solve. Then we said, let's take problems that are hard for Gurobi. Can we still embed them? It turns out not too many of them we can do on Chimera, but we can certainly embed them on Pegasus. And then there are still problems that we can't embed on Pegasus, right? And so we have to wait for the coupler to improve. Okay? So the orientation here is, I just want to find another parallel path to finding these answers in a certain period of time. Right? And I'll show you the email I got from Stanford, because he read this paper and he said, hey, can you send me the data set, and I want to do something with it. And then evidently he has an experimental machine with 200 spins and 5-bit precision of coupler, and he wants to see how fast he can do it. Okay, I want to just show you how this is done. Please hold off your questions until I go through this. So there's something called kernel. So AX equal to 0, X integer, X not equal to 0, that's called the kernel. And so what we use the quantum computer is to find the kernel of a matrix. And you can get the Graver basis from the kernel through a series of simple enough steps. Okay? So this is well-known literature. Graver basis is defined as a filtration of the kernel, and so the question is, can I get the kernel? And you'll notice that in the coming of the kernel, AX equal to 0 needs to be solved. That means the objective function is not involved, the right-hand side B is not involved. What you need is the matrix A to be embedded. For all right-hand sides B and for all objective functions, this matrix A is going to give us the Graver basis, and that is going to be our test set. Okay? So the cubo here has to be constructed. You go from integer to binary transformation. You can do binary or unary encoding. We did both. I think binary turns out to be decent enough. A cubo looks like this, basically. So if you say, how do you find the kernel of a matrix A using D-Wave? I say, convert the question kernel of a matrix into a cubo, and this is the cubo. Okay, you can, in the paper, show you the steps. Similarly, and then each time D-Wave runs it, they have 10,000 calls. Okay, each of them has a maximum of 290 microseconds, but you can keep it lower, like 10 microseconds. So if you go all the way to 290 microseconds and multiply by 10,000, that's about 3 seconds. Right? You ask me what is happening to the output. It turns out 90% of the outputs that come out of here are close enough to AX equal to 0. They'll be like AX equal to minus 1, AX equal to plus 1, minus 2. They're very close to AX equal to 0. Okay, it's trying to get you AX equal to 0, right? That's what it's trying to do. And so if you think about it, AX equal to 0 comes 11, AX with this difference being only 1 or minus 1 comes up with this. So if you say, look, if I look at AX equal to 0 with a maximum error of 3, right, in some digit, in some vector, I get, except like 10-15%, I get like 80-85%. So basically look at answers that are AX equal to 0, AX equal to 1, minus 1, AX equal to 2, 3, and you say I got about 80% of the kernel, near kernel thingy over there, okay, or approximately. Okay, it's a heuristic. Okay, and it turns out that from practical perspective, spending more time doesn't buy you much, at least at this stage. Okay, so we played around with different matrices and basically came to the conclusion that today D-Wave works well for 0, 1 problems. If you go integer 2, 3, 4, 5, 6, it starts hanging because the number of qubits you need to represent the problem is too high. The problem you can solve is too small. Right? So right now you won't use it to solve actually real integer optimization problems. You'll use it only to solve 0, 1 integer problems. Okay, that's kind of the limitation today. So to find the feasible solution, we need the right-hand side B, AX equal to B. And similarly, we figure out a cubo, and you run it on D-Wave, it gives you a bunch of solutions. Okay, just hold off the question, and then we'll come back to the end. So the basic algorithm is this. Go get some pieces of the Graver basis, go get some feasible solution, augment for a bit, and when you're done. Compare it with the optimal solution. Right? And it turns out what it can solve, it solves. And when it doesn't solve, it is because you can't embed it. Okay? So the procedure is okay. The problem on which you can apply the procedure is limited. Okay? For now. So we took some problems that have been from finance. They are known to take a long time on classical best. And we said if it takes 20 minutes on a classical best, how many seconds can it take? If it takes 8 hours, what can it take, right? And so we want to see, right, on this. And generally speaking, what we find is, where is this? Yeah. You get a whole bunch of solutions, and then about 20 or 24 augmenting steps, takes you there. Let me see if I have, I may have a comparison with Gurobi in just a bit. We can do the same thing with low span integer, but you have to reduce kind of the number of variables because the representation uses up qubits. The problem is the number of qubits in here, right? And then we basically said, what if we just called Graver once and got a partial Graver basis? We called a feasible solution once. We got whatever feasible solutions. We ran it. And in many of our experiments, this is typical, you pretty much get the optimal solution. Many of them actually get to the optimal solution. Okay. So I think 8.1 was just released recently, but 8.0 is what we ran. Okay. And we chose matrices of size, 5 rows and 50 columns from that paper. And these elements can go from 0 to t, and that t is important. Because the higher the t, the number of different jijs you need increases, and therefore when t is equal to 40, you need 1030 different distinct jijs, which is the problem in the embedding right now. So if you keep it as t equal to 6 and so on and so forth, you can go here and Gurobi is going and Gurobi is getting stuck here. And this guy, as long as your t is small, right? On D wave, it can beat all of these numbers because it only takes a few seconds, right? Each time. So D wave knows this. Everybody knows this, but without improving coupler precision, I don't see how they can actually be competitive to solve practical problems that we in operations research care about, because our matrix A is not 0, 1, but it has many elements, and the number of distinct elements Jij we need to put requires, quite a bit of precision, right? So they can increase the number of qubits, they can improve the connectivity, that's helpful, but without improving the number of distinct Jijs I can represent, my hands are tied a little bit on kind of the range of the Aij elements that can be there in a matrix, right? But the good news is if the range of Aij is small and you're dealing with 0, 1 problems, right, which does happen in some subsets, and we have, let's say, the Pegasus architecture, we can solve up to, I think this is 170 embedded in 180, we can solve up to 180 0, 1 variables, which there's no way Gurobi can do this. Gurobi chokes around 110 variables, 110, 120 0, 1 variables for these parameters. So my view is for us to beat classical in a subclass of problems, it has to be of the following type. It takes too long for classical machines, but it's embeddable in this architecture, right? And with Pegasus, I think we can find a little bit of it. But if they can improve coupler precision with this kind of connectivity in the number of qubits, we can beat classical more and more. Of course, classical will improve, and so it's a bit of a race. I was pleasantly surprised that problems of size 50 and stuff like that was actually even doable on D-Wave. Honestly, when I started with this, I thought this is such a toy thing that the only problems D-Wave can solve are what I can solve by hand, right? But the fact that it can actually solve problems that take seconds on a classical best, right, is kind of interesting. But without, I think, improvement in coupler precision, its usage will still be limited to a very narrow class problems. I think I'm running out of time, but I do want to. These are very mathy stuff. Those of you who know topology will probably see some of this and get excited. There is some. I want to close with the email I got last night. So I checked, is he a buffoon or is he real? He is real, apparently. He has a PhD from Stanford, EE. He's been postdoc at Stanford. He's got about 2,000 citations of his 3 or 4 science and nature papers. So I think he's considered let's say, a real scientist of sorts. So I've been communicating with him, and I'm hoping that we will send him some of the instances that we have created. We know what it can or cannot do in D-Wave Chimera. We know what it can or cannot do in Pegasus. And he's going to see what he or cannot do. From his email, it appears that he can go up to 200 spins. But I haven't spent more time on this. So, think of this as very early computational work on available hardware, right? And trying to figure out, so what can it do today? What would it take for it to do something interesting from a business perspective, right? And I think I'm hoping that as time goes by, each of these will have better and better architectures, and at some point, right, the promise is they're supposed to beat classical methods. Let me take your question and then stop.
Why don't we thank
Okay.
the speaker now?